imagine you have a perfect cube. Now take a saw and cut it into a finite number of smaller cubes. They don't all have to be the same size, just perfect cubes. Here is the question. Is it possible to do this cut so that every single small cube has a different size? Or must at least two of them always be equal? Pause and think. The answer is surprising, and the proof is one of those beautiful arguments that feels almost magical. The claim is this: no matter how you dissect a cube into a finite number of smaller cubes, at least two of them must have the same side length. In other words, a perfect heterogeneous cube dissection, where every piece is a different size, is impossible. We will prove this by contradiction using a beautiful technique called infinite descent. Assume for contradiction that we have a valid dissection where all small cubes have distinct sizes. Look at the bottom face of the big cube. Each small cube that sits on the floor contributes a square footprint to this bottom face. These square footprints tile the bottom face perfectly. No gaps, no overlaps. So we have a square tiled by smaller squares, all of different sizes. Now focus on this square tiling of the bottom face. Consider the smallest square in this tiling. I claim it cannot touch any edge of the big square. Why? Because if it touched an edge, the squares adjacent to it along that edge would each be larger, and their combined width along the edge must exactly fill the remaining space. But a smaller square hemmed in by larger squares along an edge creates a geometric contradiction with the tiling. Therefore, the smallest square must lie strictly in the interior of the bottom face, surrounded on all four sides by larger squares. Now here's the key step. Look at the top face of the smallest cube, the one we just identified sitting in the interior. Its top face is a small square, completely surrounded by the walls of taller cubes on all four sides. So the small square on top must itself be tiled by the footprints of even smaller cubes sitting on top of it. In other words, the top face of our smallest cube is a square tiled by even smaller squares, and once again, all with distinct sizes since we assume that globally. But now we are in the same situation again, one level up. We have a new square tiling, and by exactly the same argument, the smallest square in that tiling must lie in the interior, with an even smaller square on its top face, creating yet another tiling of a smaller square. This chain never stops. Each step produces a strictly smaller cube, giving us an infinite, strictly decreasing sequence of cube sizes from a finite collection of cubes. That is impossible. This is the contradiction. We started with a finite set of cubes, but our argument produced an infinite, strictly decreasing chain of side lengths, all drawn from that finite set. A finite set cannot contain an infinite, strictly decreasing sequence. Therefore, our assumption that all cubes have distinct sizes must be false. At least two cubes in any dissection must share the same size. QED. What I love about this proof is that it turns a three-dimensional question into a two-dimensional one, and then uses infinite descent to finish it off elegantly. If this gave you a spark of mathematical joy, hit like and subscribe for more visual proofs. Drop in the comments. Did you guess the answer before the